Good afternoon. We welcome you all for the afternoon session of ATAL sponsored 1-week faculty development program on sensor technology. It's my immense pleasure to introduce our today's chief guest, Dr.S. Selvaperumal sir, Professor and Head of Department EEE, Syed Ammal Engineering College, Ramanathapuram. He has completed his BE Electrical and Electronics Engineering at Tyagaraja College of Engineering, Madurai, and ME in Power Electronics and Drives at PSR College of Engineering and Technology, Dindigul. He has obtained PhD in the year of 2013 from Anna University in the Faculty of Electrical Engineering. He has more than 15 years of experience in teaching and 8 years of experience in the field of industry. He published more than 60 articles in reputed journals, including IET and IEEE Transactions, as well as he has published 16 textbooks in the field of electrical engineering for the benefit of rural students' academic career. He has filed 21 patents and received the 4 copyrights from Copyright Office, Government of India, New Delhi. He has the Google Scholar Station indices with 407 and H index with 12. He has the cumulative impact factor with more than 30. He is acting as a recognized supervisor in Anna University and guiding 10 PhD scholars and produced 9 PhD scholars in the Faculty of Electrical Engineering. He is acting as a guest editor in Current Signal Transaction Therapy and Medical Image Review in Bentham Science, USA. He has acted as an editor in Applied Mechanics and Material Journal, Switzerland. He has received funds from various funding agencies like AICTE, TNSCST, and he is acting as an editorial board member and program committee member for the various reputed journals and international conferences. He has been received Best Academic Circuit Faculty Award from ASDF SIAA USA in the year of 2018. He has been awarded and recognized as an outstanding reviewer in the year of 2010, 2011, 12, 13, and 14 in the International Journal of Computer and Electrical Engineering and Engineering and Technology. He is acting as a reviewer for IEEE, IET, other reputed SEI journals and international conferences, and he has organized 2 international conferences. Now we invite Dr.S. Selvaperumal sir to share his research ideas in the field of half-effect current sensors for power electronics applications. Welcome you, sir.
Yes, ma'am. Thank you for your introduction. First of all, I would like to sorry for the inconvenience.
No
now
problem, sir.
late, right. Okay. So first of all, I would like to thank the management, the principal, and ASTE for giving wonderful opportunity to deliver the lecture on the topic of Hall effect current sensors for power electronic applications. Right? So since you are all electrical engineers, you may easily give the answer to my questions. So listen, the situation. In a kitchen, tube light is on. By the time you are putting the rice inside the grinder and switch it on. So what change you can find with the tube light when the grinder is on? So when you switch on the grinder with load, the tube light will get flicker. That is, it will become dim. Somehow we will manage and complete the task. So this is analogy to the handling of afternoon class. So handling afternoon class is really a tough task. Your stomach is like a grinder and the brain is like a tube light, right? So when you finish lunch, your stomach is overloaded, so the brain will become dim. So as an electrical engineer, if you make your brain bright, our job will be very easy. So please be alert. We will get discuss. We will get success in our task. Right. The next slide. Okay. What are the prerequisites? We are in need the knowledge about electrical engineering, power electronics, control theory, digital signal processing, and MATLAB. Right. The next slide. At the end of this presentation, participant will be able to develop a methodology for compensator design of a closed loop Hall effect current sensor, keeping its step response characteristics as design attributes, and also able to fabricate a controllable current sensor in practical for experimental verification of the steady state and the transient performance of the current sensor. Next slide. So topics for discussion: introduction about Hall effect sensors, compensator design for closed loop, power electronic converter for characterization of Hall effect sensor, practical current sensor, and then conclusion. Right. So next slide. Okay. So current sensors are widely used in industrial electronics and scientific instruments. So their major applications include practical accelerator, beam instrumentation, plasma research, electrical surgical analyzer, CT scan machine, lightning discharge, EMI industry, high voltage surge current testing, automotive electronics, electric drives, power converters, and power systems. So these are some applications, right? So bandwidth, precision, construction, compactness, and the galvanic isolation requirement very based on the applications. So output of the sensors may be used to monitor current or as feedback signal in current loop. We know that. So galvanic isolation and the voltage insulation level are other important criteria of selection of current sensors in high voltage, high current applications. In most of the applications, only AC suffers AC sensing, right? So while in few but the critical applications, the sensor is required to sense both DC and AC with sufficiently large bandwidth. Okay, so sensors used in pulsed operations are expected to have very small rise time of the order of 1 millisecond. Sorry, 1 nanosecond, right? So current sensing techniques used in the aforementioned applications are enlisted in the slide, right? So with DC or AC current sensing capability and the galvanic isolation property, right? So these techniques can be broadly classified into 4 categories. So Ohm's law of resistance, Faraday's law of induction, magnetic field sensors, magneto-optic effect. Right? The next slide. So current sensors find frequent use in power electronic applications. It includes current or torque control of electric motors, current control in grid connected converters, uninterrupted power supply, resonant converters, current mode control of DC to DC converters, short circuit protection of power converters, short circuit protection of power devices, inner current measurement in power system. Right? So here a few waveforms of electric currents in power electronic applications are shown in the slide. So waveform shape, magnitude, and the frequency of electric currents in power converters are required to determine efficiency, harmonic distortion, electromagnetic compatibility, semiconductor switch stresses, etc. Right? The ultimate objective of power electronic study is to convert electric energy into useful form in the most efficient manner, right? So the efficient power conversion requires both voltage and current data. So unlike voltage sensors, current sensors, when integrated to power conversion system, often need to intrude to the current carrying circuit, which may affect the actual current sensing. Right? So a number of current sensing techniques exist these days. A particular technique may be selected for use in power electronic system based on its required role. Application of current sensors in power electronics may be broadly categorized into three types: current control, current monitor, and fault protection. We will discuss one by one. Right? Next slide. Current control. So we know that electric current is essential driving factor in electromechanical energy conversion. Interaction with magnetic field creates electromagnetic force or torque, which facilitates conversion of mechanical energy into linear or rotary motion, respectively. Applications of electric motors range from huge marine electric propulsion motor to small spindle motor in hard disk of computer, from heavy duty drilling motor in mines to light rotary motor in domestic applications, right? So most of these applications require controlled torque and speed, right? Which in turn require control of electric currents. So apart from electromechanical energy converters, electric power may be further converted using power electronic converters from DC to AC converter, or AC to DC converter, DC to DC converter, AC to AC converter, based on applications, right? So these converters are the main parts in solar and wind energy conversion, grid integration, power conditioners, and various utility equipments, right? So the size of the converters ranges from a small regulator module in an electric gadget to large power conditioner in HVDC application, right? So in most of these converters, current controllers are required to produce current to desired shape and frequency, right? So isolated current sensors, especially Hall effect current sensors, are widely used in current control of electric drives, grid interactive converters, active power filters, and other high power, low voltage power electronic systems, right? So in high power converters, the switching frequency is the order of 10 kilohertz, right? So bandwidth of Hall effect sensor is typically 200 kilohertz and can be employed in the feedback of these converters. In addition to high bandwidth, the Hall effect sensors have DC or AC measuring capability and provide galvanic isolation as well. So their construction is robust and can be used in field applications. In non-isolated DC to DC converters, shunt resistors are frequently used in current mode controllers and other current control schemes, while magnetoresistive sensors and miniature Hall effect current sensors find place in isolated DC to DC converters, right? Next. So next one is current monitor. In most of the power electronic systems, the current is needed to monitor to validate the theoretical analysis with the experimental results. So the bandwidth of sensor in monitoring application is usually higher compared to that used in current controllers. So high bandwidth current sensors are called current probe and have a special signal conditioning circuit to reject unwanted measurement noise. So these probes have a special output port to be used in oscilloscopes, right? So Hall effect current sensors are widely used to monitor currents in electric motors and power converters. Typical bandwidth of these sensors is 200 kilohertz, which is sufficient enough to capture DC to AC current with the switching ripples. In resonant converters, the fundamental frequency of the current may go as high as 1 megahertz, and the current transformers find frequent use in these converters. Here, four special applications involving current monitoring. One is PCB based power converters, switch current, pulse current, and EMI test. Right? Next slide. So in printed circuit boards, there are always phase constraint and limitation on heat dissipation. The current sensors used in PCB are expected to be compact in size and work satisfactorily with the natural cooling. Shunt resistors are very common in PCB current sensing, but they dissipate considerable heat at large current. Right? So linear Hall integrated circuit based sensors and magnetoresistive sensors have inherent galvanic isolation and are usually employed where high bandwidth and DC or AC measurement capabilities are required. So these sensors are available commercially with the current measuring range up to 100 ampere and consume minimal power even at large currents, right? So linear integrated circuit based current sensors have typical bandwidth of 100 kilohertz, while magnetoresistive sensors bandwidth is relatively high, up to 2 megahertz. So shunt resistors, linear Hall integrated circuits sense field effect transistors, magnetoresistive sensors, and current transformers are used without signal conditioning circuit to monitor currents in automotive and low power electronics. So current transformer based sensors are also used in printed circuit board based DC to DC converters to measure average inductor current. So to be operated in an ambient temperature of 250 degrees centigrade, a novel bidirectional saturated current transformer based sensor is used. Right? The sensor is mounted on the leg of discretely packaged SiC device, right? Silicon carbide device, and can measure DC and sine wave AC, sinusoidal AC up to 1 kilohertz and 50 ampere. Right. The next slide. Switch current. So to determine the switching losses in semiconductor devices, the switching current needs to be monitored. So with the advent of modern power devices capable of switching as fast as in 10 nanoseconds, the current sensors response time and rate of change of current with respect to time, di by dt rating must be sufficient to capture that current. So owing to inherent galvanic isolation and high bandwidth, Rogowski coil based current sensors are usually employed in industry to observe switching current. But intrusion of the coil in the switching circuit inserts inductance and hence affects the actual switching current waveforms. So it also increases the voltage overshoot across the switching device. Coaxial current transformer is a practical solution used to monitor switching current in high power converters with minimal insertion inductance, right? Next slide. So third technique is pulse current. So capacitive discharge and surge current testing need current sensors designed for pulse current monitoring. So current transformers and Rogowski coils are usually employed in these applications. In HVDC systems, the current level may go as high as 500 kiloampere. Fiber optic current sensors are used to monitor bidirectional DC up to 500 kiloampere with high level voltage isolation and good immunity to electromagnetic interference. In low voltage applications, shunt resistors are also used to monitor pulse current, but their use is often limited by the pulse heat dissipation represented by I square RT rating, right? A combination of Hall effect sensor and current transformer is used in designing a current probe capable of measuring both DC and AC up to 40 ampere current and the bandwidth from DC to 30 megahertz. Right? So owing to small size and high bandwidth, magnetoresistive sensors find frequent use in brushless DC motor, special machines like BLDC motor and switched reluctance motor to sense square-shaped current. Right. So next slide. The EMI test. So electromagnetic interference test is an important application where the current as low as 10 microamps and the frequency as high as 200 megahertz may be required to be monitored. So these current probes are normally designed using current transformers. Right. Next slide. So the slide shows fault under load test waveforms. IGBT current is denoted as IC is 200 ampere per division, and collector emitter voltage 100 volt per division. Gate emitter voltage is 10 volt per division. Time is 500 nanosecond per division. Right. So the IGBT current reaches 1200 ampere within 1 microsecond before the short circuit fault is removed by turning off the gate pulse. So here the dynamic performance of current sensors play a crucial role in fault protection system of motors and power converters. The protection system sends shutdown signal on either overcurrent or short circuit fault. So output of the current monitors can be used in overcurrent protection. So in short circuit protection of power semiconductor devices, the sensor must respond very fast as the device can survive the fault current lasting for only few microseconds. Right. So the IGBT current reaches 1200 ampere within 1 microsecond before the short circuit fault is removed by turning off the gate pulse. So DI by dt tracking capability of the sensors must be sufficiently high to track the short circuit current. Shunt resistors, current transformers, and Hall effect current sensors are usually employed in short circuit protection of power electronic circuits. So nowadays, some IGBTs have inbuilt sense resistor in the output part to be used for overcurrent and short circuit protection. Next slide. So Hall effect current sensors. So Hall effect based sensing devices are widely used in keyboards, position sensors, proximity sensors, speed sensors, magnetic cord readers, flow rate sensors, automotive sensors, current sensors, etc. So general features of Hall effect based sensing devices are true solid state, long life, high speed operation, no moving part, broad temperature range like minus 40 degree Celsius to 150 degree Celsius, and highly repeated operation. Right? So, in addition to these features, Hall effect current sensors utilize static and dynamic magnetic field measurement capability of Hall effect based magnetic sensors to measure both DC and AC. Right? So, the magnetic field produced by the current to be measured is sensed by a Hall effect magnetic sensor whose output gives indirect measurement of the current. More details about Hall effect based sensing devices and their applications in current sensors are given in some references, right? So the operating principle of Hall effect current sensors used in power electronic applications is briefly discussed in the following slides, right? Next slide. So a Hall element, also called a Hall effect magnetic sensor, is a transducer which produces output voltage in response to applied magnetic field, right? So it is made of semiconductor or metal alloys. So it uses the Hall effect phenomenon of metals and semiconductors to sense the applied magnetic field. Right. Hall effect was discovered in 1879 by Edwin Herbert Hall. So when a magnetic field B is capital B is applied to a metal or semiconductor, and if the charge carriers are moving with the speed small v, that is by applying an electromagnetic force, they experience force. So force is equal to QV into B, and drift towards the direction of force. The accumulation of these carriers create electric potential, right, across the two parallel sides of the Hall element. This is shown in the slide, right? So this potential is directly proportional to the perpendicular component of the magnetic and the biasing current, right? So the resultant output voltage is given as second equation, VH is equal to RH IC into BH, right? Where RH is the Hall efficient. So it is constant for a wide range of BH and varies with temperature. So if the biasing current IC is maintained constant, the output voltage gives direct measurement of the applied magnetic field. Structure fabrication. Okay. So if the relationship between an electric current and the magnetic field produced by the current is known, the same Hall element can be used to measure this current also, right? So for example, it is known that magnetic field produced at distance d by a conductor carrying IP current is, go to the next slide. So this is the example. It is known that the magnetic field produced at this distance d by a conductor carrying I suffix P current is, then magnetic flux density B is mu naught divided by 2 pi d into IP. So provided the distance d is very small, if a Hall element is placed perpendicular to this magnetic field, right? So this is shown in the slide, and biased with the constant current IC, the sensor output voltage can be given as second equation, VH is equal to RH IC mu naught divided by 2 pi d into IP, right? So in this way, VH gives measurement of the current IP. To make VH linearly dependent on IP, the distance D must be maintained constant. This type of current sensing technique is used in PCB current sensors. So where current carrying track and Hall element both are mounted on fixed positions, right? So next slide. So in another arrangement, the Hall element is placed in the air gap of a magnetic core. This is shown in the slide figure A, right? The air gap is kept very small compared to length of the core, right? The magnetic core acts like a flux concentrator. Permeably iron 80% of nickel provides very low coercive magnetic field Hc in the wide operating temperature like minus 40 degrees Celsius to plus 140 degrees Celsius, and is normally used for the magnetic core in Hall effect sensors. It improves linearity and accuracy of the sensor, right? So ignoring fringing effect in the air gap, the magnetic field in the gap can be assumed to be uniform and perpendicular to the plane of the Hall element. This is shown in the slide figure B, right? So the magnetic field in the air gap can be expressed as the equation given in the slide. So Pg is equal to mu naught Ip divided by Ig is equal to Bh. So normally the distance D in the slide, previous slide, is of the order of few centimeters, whereas in this case, next slide, so Lg is in a few millimeters only, right? It makes the magnetic field produced over Hall element for the same value of Ip much larger compared to that in previous arrangement, right? So the previous figure, right? So in this way, the sensitivity of the current sensor is improved. Also, very high permeability of the core, keeping the magnetic flux confined within itself and the air gap only, right? So if the air gap is very small, the position of the current carrying wire in the empty inner space of the core does not affect the flux distribution significantly, and hence the expression of Bg, right? So this fact can be utilized to build a clamp-on current sensor, which is very convenient for monitoring currents in industrial applications. Okay. Next slide. Okay. So the output voltage of the Hall element consists of two components, common mode, that is Vcom, and differential mode Vh. So only Vh responds to the changing magnetic field. The magnitude of Vh is the order of millivolt even for a large current. A differential amplifier with high CMRR is required at the output of the Hall element to bring the amplified output voltage V amp into proper measuring range. So normally operational amplifiers are used to amplify Vh. In high precision application, instrument amplifiers are used, right? So the configuration of the sensor shown in the slide, this is known as open loop Hall effect current sensor, right? So as evident from the configuration, the output signal is voltage signal. The losses in the amplifier and in the magnetic core contribute to its total power consumption. Right. Next slide. In open loop current sensors, when the current is large, the core flux becomes high and may saturate. So this operating point may deviate from the linear range of BH curve, resulting in non-linear VH, right? So also the saturation flux density of the core puts restriction on the upper limit of the measured current. So for example, if the core is nickel iron alloy or iron nickel alloy with the saturation flux density is 600 millitesla at 25 degrees centigrade and the air gap length of 0.5 millimeter. The maximum current that can be measured will be approximately 240 ampere, right? So, but the BH curve becomes highly non-linear near to B saturation, right? So, to avoid non-linearity, the current sensor should be operated near to what is called zero flux density of the core. Okay. So to maintain zero flux in the core, the open loop configuration is modified to accommodate a compensating winding as shown in the slide, right? So instead of amplifying and measuring VH directly, it is passed through a compensator, GC of S, whose output is fed back through compensating winding to produce counter magnetic flux in the core to nullify the total flux, right? The voltage drop across this burden resistor RB reflects the measured current IP. This configuration is known as closed loop Hall effect current sensor. Due to operation near zero core flux, they are also known as zero flux type Hall effect current sensor. The compensator GC of S is usually implemented with operational amplifiers. A current booster amplifier is employed at the output stage of the compensator to cater the high values of I2. The output signal in this configuration is current, due to which the power consumption increases with the magnitude of the primary current, but the linearity and the accuracy of these sensors are much better compared to open loop configuration, right? Designing of these sensors mainly involves a proper choice of compensator GC of S, number of turns in the compensating winding, and value of the burden resistor. So biasing of the Hall element requires careful design of the electronic circuitry, considering the effect of ambient temperature, right? So few important parameters of open loop and closed loop current sensor are compared and enlisted in the next slide. Go to next slide. Nowadays, closed loop Hall effect current sensors are available up to 10,000 ampere, right, or 10 kilo ampere measuring capability. Typically, the bandwidth is from DC to 200 kilohertz, while in few designs the bandwidth of 300 kilohertz. If cost and power consumption are not in consideration, closed loop sensors are preferred over the open loop sensors, right? Next slide. So in open loop current sensors, the Hall element is solely responsible for measurement of both low and high frequency primary current. Its performance gets damaged at high frequency due to thermal drift, non-linearity, and limited bandwidth of the Hall element, and the amplifier circuit, right? So these effects are minimized in a closed loop sensor by using the compensating winding, where Hall effect takes care of low frequency measurement, and the current transformer effect comes into picture for high frequency measurement, right? So, but the power consumption increases due to output current signal. A novel configuration was proposed, right? So, where the output voltage of the Hall element and the current transformer winding are amplified and added using an electronic adder to get the final output voltage. So, this voltage signal proportional to the primary current, right? So, this configuration was further modified to get the bandwidth of 30 megahertz, right? So, similar to the aforementioned configurations, a novel configuration is designed and commercialized by Lum Instruments. This is shown in the slide, right? So it uses the low frequency measurement capability of open loop sensors and high frequency accuracy provided by current transformer. So the two outputs are added electronically to get a final output voltage signal. So its performance and the cost are comparable to closed loop sensors. As the output signal is voltage, its power consumption is lower compared to closed loop sensors, right? So next slide. So Hall effect current sensors are widely used in power electronic applications as a key element of control loops. Example: current, torque, force, speed, position are in current display systems. So owing to inherent galvanic isolation, the toroidal structure and DC or AC measuring capability with high bandwidth, these sensors get an advantage over other current sensing techniques. So the applications of Hall effect current sensors in power electronics are listed here. Some of applications: electric drives for the control of phase currents and torque, frequency converters for the control of output current and DC bus current, grid interactive inverters for control of grid currents, power factor correction circuits for monitoring mains current, power conditioners for the control of fundamental and harmonic currents, UPS or other battery operated equipment for the control of charge and discharge currents, servo motors used in robotics for high performance speed and position control, special wide bandwidth power supplies used in radar, and also automotive electronics for motor drives and battery current control, protection of power semiconductor devices from output short circuit fault, electric traction system, track side circuit breaker and rectifier protection, rolling stock traction converters and auxiliary power supplies, energy management system, switching power supplies, electrolysis equipment and other applications, right? So go to next slide. So characteristics of Hall effect current sensors. So here the Hall effect current sensors measure DC or AC and the complex current waveforms with galvanic isolation. There is always a limitation on primary current that can be measured with any thermal or electrical failure. The accuracy and the linearity parameters are important in high precision applications like speed or position control of servo motor drive. The operating range of ambient temperature should also be specified to protect the Hall element and internal electronic components. The dynamic performance affects the performance of the current control loop in which they are employed. Right? The characteristics of Hall effect current sensors are in general, any DC or AC current sensor can be broadly represented by two behaviors. We know that one is steady state behavior and another one is dynamic behavior. Right? So go to the next slide. So steady state behavior can be characterized by the nominal current rating, measurement accuracy, linearity error, power consumption, and the ambient temperature range. So the nominal current rating can go up to 10,000 amps. Closed loop sensors have better accuracy, error less than 1% compared to open loop counterparts, error of the order of few percent. So normally these sensors can operate from minus 40 degrees Celsius to plus 85 degrees Celsius ambient temperature. In automotive applications, the upper limit can be raised up to plus 125 degrees centigrade. But the bandwidth goes down due to increased core losses and reduced margin of heat dissipation in internal electronics. Right? Next slide. So this is the dynamic behavior of Hall effect current sensors. Can be characterized by its bandwidth and step response. Right. So the slide shows typical parameter defined to characterize step response of current sensor. Response time denotes T suffix RES. This is the response time, and di by dt, rate of change of current with respect to time, following capability are often used to quantify the step response. So bandwidth, higher bandwidth results in better step response of the sensor. So bandwidth of Hall effect sensors is often limited by the processing electronics and the core losses. So typical bandwidth of open loop and closed loop sensors is 50 kilohertz and 200 kilohertz respectively, right? So open loop sensor is 50 kilohertz and closed loop sensor range is 200 kilohertz. So a current sensor's response to a step current with controlled rate of change is characterized by the response time. So it is the delay between the primary reference current reaching 90% of its final value and the sensor's output reaching 90% of its final value. Right. So during this measurement of the reference current shall behave as a step current for closed loop and open loop sensors. Its typical value is for closed loop typical value is 1 microsecond and open loop value is 5 microsecond. Right. So di by dt following, it characterizes the sensor's ability to follow a fast change in primary current. Right. So it is mainly governed by the high frequency disturbance created by external conductors. The routing of sensor output wires and paths of PCB track at the output limit the di by dt following capability of the sensor. So the output wiring should have minimal loop area to improve rate of change of current with respect to time. So this characteristic is important in monitoring current for short circuit protection of power devices. Right. A typical value of di by dt following capability of Hall effect current sensor is 50 ampere per microsecond. Right. So the dynamic performance of Hall effect current sensor is strongly affected by the location of the primary conductor with respect to the air gap in the magnetic core. So increasing the air gap reduces the effect of non-linearity caused by the non-homogeneity of the magnetic core material. But larger air gap leads to unwanted sensitivity to the position of measured conductor. Right? So fringing of the field in the air gap reduces natural shielding of the toroid from unwanted external magnetic field. Right? So next slide. The performance validation of Hall effect current sensors. A current source is required to verify the transient and the steady state performance of Hall effect current sensors. To verify the transient performance of current sensor having response time less than a specified value, the current source must be able to produce a step excitation current having step transition much less than specified response time, so that it would emulate step input to the sensor. It should also generate a step current with control rate of change to find out parameters shown in the previous slide, right? So the di by dt of the step current should be greater than the rate of value to check the limitation in accurate di by dt. So to check minus 3 dB bandwidth, go to previous slide. So to check the minus 3 dB bandwidth of the sensor, a network analyzer can be used to exit the sensor, and the response plot can be obtained for frequency ranging up to order of megahertz. The excitation current in network analyzer is of the order of 100 milliampere, which is very small compared to typical current rating of the current sensor. Right? So the linearity and the accuracy of the sensor output must be verified for the DC excitation at rated value. To verify all these steady state characteristics, the current source should be able to produce DC and sinusoidal reference current at the rated value with variable frequency up to sufficiently large value. While generating continuous sinusoidal current, it should draw minimal active power from the main supply to reduce the electricity consumption during the heat run test. Next slide. So an objective of this presentation is to design high performance closed loop Hall effect sensors and to verify its performance. Existing current sensing techniques in power electronics are classified based on the applications. Working principle of existing Hall effect current sensors is discussed briefly. Applications of these sensors in power electronic applications is listed. Steady state and dynamic characteristics of Hall effect current sensors are discussed. To validate these characteristics, a current source is suggested with required details. So performance of open loop and closed loop Hall effect current sensors is compared and found that closed sensors have higher bandwidth, and it can be further improved by careful design of current transformer structure. Go to next slide. Next slide. Okay. So this is a compensated design for closed loop Hall effect current sensor. Following overturn slides. So current sensors are widely used in power electronic systems, including switched mode power converters, electric machine drives, grid connected power converters, etc. We already discussed it, right? So a number of these applications require current measurement with galvanic isolation. Current transformers cannot measure direct currents and have large error at low frequency alternating currents. A modified current transformer structure using Hall element, also known as Hall effect current sensor, is commonly used in isolated current measurement applications. So this study involves analysis to develop high performance DC or AC current sensor with performance comparable to commercially available current sensors, right? So in this presentation, operational principle of closed loop Hall effect current sensors. An equivalent circuit is derived using some practical assumptions which facilitates the analysis of these sensors. So closed loop form analytical expressions of step response are derived for the current sensor with a proportional and PI compensator. This is used to show the effect of designing the control parameters on the dynamic performance. Based on these expressions, a procedure is devised to tune the parameters of proportional integral compensator for high precision current measurement. A prototype current sensor is built in laboratory and test to validate the analysis, right? So next slide. So these are the sum of symbols and abbreviations. I1, small I1 is primary current to be measured. I2 is secondary current, small n1 number of primary turns, small n2 number of secondary turns. Phi C is magnetic flux in the core. Lambda 2 is flux linked with secondary coil. Bg is magnetic flux density in the air gap. Hg is magnetic field intensity in air gap. Ig is air gap length, and like this, right? So next slide. Modeling of the current sensor. A closed loop Hall effect current sensor is shown in the slide. A Hall element is inserted in the air gap. A conductor carrying current I1 creates a magnetic flux in the core and the air gap. The Hall element produces voltage VH in response to the air gap magnetic field, which is further amplified by the compensator GC of S in order to produce counter magnetic flux. In the core, right, due to compensating coil current I2. So this ensures that the excitation of the magnetic core is small and lies in linear region of the BH curve of the core material, right? So some of the assumptions to model the current sensor, the following assumptions are made, right? I'll go to the next slide. Relative permeability of the magnetic core is very high. Leakage inductance and the interwinding capacitance of the compensating winding are ignored. Position of the conductor with respect to central axis of the core doesn't affect the magnetic flux distribution. Presence of the Hall element in the air gap doesn't disturb the field distribution in the air gap. Fringing effect in the air gap is ignored. So these are the some of the assumptions to model the current sensor. Hall effect current sensors are mostly used to sense switching ripple currents of switching converters, grid frequency currents and their harmonics. So typical bandwidth of Hall effect current sensor is 200 kilohertz. So switching frequency in power electronic converters may go up to 100 kilohertz. So the non-idealities associated with the sensor become significant in the frequency range greater than hundreds of kilohertz. So hence the above assumptions are relevant from the perspective of power electronic electronic applications. Go to next slide. So applying Ampere's circuital law and ignoring reluctance offered by the magnetic core, we get the equation 1. So using the assumptions 4 and 5. So what is 4? 4 is presence of the Hall element in the air gap, does not disturb the field distribution in the air gap. Fringing effect in the air gap is ignored, is fifth assumption. So using the assumptions 4 and 5, the core flux can be expressed as phi c is equal to Bg into AC, and expand Pg and AC. So we will get the equation 2.3, right? So where Im and Lm is given in equation 2.4. So Im is the magnetizing current and Lm is the magnetizing inductance. So both refer to secondary side. Okay. So the voltage induced in secondary winding can be written as the equation 2.5. Go to next slide. So as per configuration of the current sensor setup shown in figure 2.1, right? So we will get the equation 2.6 and 2.7. So based on equation 2.3 to 2.6, the equivalent circuit model of the current sensor can be represented as next slide. Go to next slide. Okay. So output voltage of Hall element VH is given by the equation 2.8. So KH into phi Z divided by AC. Using the equation 2.3, VH can be expressed as equation 2.9. So VH is the feedback signal corresponding to Im. It passes through the compensator Gc of S to change V amp of S, and in turn reduces phi C. So the signal propagation through the Hall element channel is shown in the next slide. Go to next slide. So the upper figure, right? The signal propagation through the Hall element channel is shown in the slide. So using equation 2.7, 2.8, the equivalent circuit can be represented in S domain. As a block diagram is shown in the figure B, 2.3b. Okay. So for accurate measurement of I1, the secondary current I2 should be ideally equal to N1 by N2 into I1. So in other words, the magnetizing current Im and hence the core flux phi C should be brought down close to 0. So the role of compensator Gc of S may be understood with the equivalent circuit shown in the previous slide. The voltage source V amp is a function of VH and the Gc of S. This is expressed in equation 2.7. At low frequency, the reactance associated with the Lm become very small. In absence of V amp of T, the magnetizing inductance draws huge Im, and hence the error in I2 of T becomes large at low frequency. The compensator Gc of S generates sufficient voltage to reduce V2 across Lm. So and hence Im. So at high frequency, the reactance of Lm is high, and the Gc of S does not need to play any compensator's role to make Im small. The CT action takes over Gc of S at high frequency. The role of Gc of S is clearly visible in the block diagram 2.3b. This is a unity feedback closed loop reference tracking control system. The forward path consists of two parallel paths, namely the current transformer channel and the Hall element channel. Forward gain must be very high in the desired range of frequency. The Hall element channel enclosed with dotted line is responsible for high gain required in low frequency range, while the block N2S provides that required high gain in high frequency range. Right? So the effect of GC of S may be explained analytically. So using the block diagram, write the transfer function I2 of S by I1 of S is equal to N1 by N2 into H of S by 1 plus H of S. Right, this is the equation number 2.10. Go to next slide. So under the measurement error, function is given by the equation 2.11, where H of S equal to Lm by RL into S plus Km into GC of S. This is shown in the equation 2.12. So go to next slide. So based on equation 2.11, to bring Im close to 0, H of S must be large over the whole frequency range. H of S can be further split into two parts as the equation 2.14. Okay. So HCT of S plus HE of S. So in this equation 2.14, HCT of S reflects current transformer action, while HE of S accounts for the compensation provided by the Hall element. Right. So at low frequencies, HCT of j omega is very small. So without HE of S, the magnitude of H of S also becomes small. So due to the same reason, current transformers are not used to measure direct and low frequency AC. Right. So the compensation HE of S is chosen such that its magnitude is large at low frequency, which can be done by proper selection of GC of S. Right. Go to next slide. In closed loop Hall effect current sensors, the magnetic core should be excited close to zero core flux. The constituent HT of j omega of H of j omega is very large at high frequency, but almost negligible near DC. So it urges the choice of GG of S to be such that it results in large value of HE of j omega at low frequency. Sorry. The compensator GC of S can be chosen as either of the following classical compensators. Right. The proportional and the proportional integrator. Right. So PRPI. So we see one by one. Go to next slide. Okay. So using GC of S is equal to Kp, the equation 2.1 into rewritten as the equation 2.15. Right. So where H of j omega has finite value, K for omega is less than Km Kp. It results in constant non-zero value of Im, which reflects a steady state deviation in I2 from I2 star. This is nothing but N1 by N2 into I1. So we return as 2.16. Right. So an obvious choice Kp should result in large magnitude of H of S in the flat region, right? So this is shown in next slide. Go to next slide. So the value of Kp may be selected based on the dynamic performance of compensated current sensor. A step response is simple choice to measure the dynamic performance. For a step jump input I1 of t at t is equal to 0, that is I1 of S is equal to I1 by S with 0 initial condition, and using equation I think 2.10 and 2.15, then we will get equation 2.17. Go to next slide. Okay. So equation 2.17 shows that there is always steady state error in I2 of t. A very high value of Kp is preferred to confine the error to a chosen tolerance limit. The maximum value of Kp is limited by the practical implementation of GC of S using operational amplifiers. Go to next slide. So using GC of S is equal to Kp plus Ki by S in equation 2.12, we get equation 2.18 and 2.19 and also 2.20 and 2.21, right? So the compensator parameters Kp and Ki can be decided if eta h and omega n are known. So these values are chosen based on magnitude frequency response of H of S in conjugation with step response of the compensated system. As discussed in previous slides, H of j omega should be kept high throughout the frequency range of interest to minimize error in alternating current measurement. So for a step jump in I1 of t at t is equal to 0 with 0 initial condition, I1 of S is equal to I1 by S using equation 2.10 and 2.18, then we will get the equation 2.22. Go to next slide. So I2 of S, right? So where eta n is Km Kp plus RL by Lm divided by 2 omega n, right? And omega n is given by 2.21, the equation 2.21. So the second term in equation 2.24 represents the fractional error in I2 of S. So based on the damping factor eta n, the step response may become under damped, that is eta n less than 1, critically damped, that is eta n is equal to 1, or over damped, eta n is greater than 1, right? Go to next slide. So this slide shows the step response 3 conditions for a fixed value of natural frequency omega n, right? So to avoid large peak overshoot in I2 of t, we can select eta n greater than or equal to 1, but this would increase the settling time. Okay, so a high value of eta n requires high Kp as expressed in the equation 2.25. So implementation of PI compensator using operational amplifiers puts limitation on maximum value of Kp, choosing eta n is equal to 1. So avoids that complexity and provides lower settling time. So using eta n is equal to 1, in equation 2.24, then we will get the equation 2.26. Go to the next slide. So taking inverse Laplace transform of 2.26 gives the equation 2.27. I2 of t has minimum value I2 min at t is equal to t min, where we will get the equation 2.29. So what is the inference from the equation 2.29? So small e is the base of natural logarithm. So very low value of t min and the error in I2 of t are desired for fast dynamic response, right? So this is shown in the slide. It can be achieved with a large value of omega n, as shown in equation 2.28 and equation 2.29. Go to next slide. So figure A shows the effect of increasing omega n in the step response. It can be seen that high value of omega n results in reduced error with low settling time. So if Kp and Ki are selected such that Kp, Km greater than RL by Lm, so we can approximately eta h in equation 2.20 as equal to eta n. So we get eta h approximately equal to 1. So a Bode magnitude plot of h of j omega is shown in figure B. For eta h is equal to eta n and also equal to 1. So increasing in the value of omega n increases the minimum value of h of j omega. So this reduces the error in measurement of sinusoidal I1 of t throughout the frequency range of interest. So omega n is selected based on either the value of t min or the maximum understood allowed using equations 2.28 or 2.29. So the PI compensator parameters Kp and Ki are calculated using the equations 2.21 and 2.25 with the eta n is equal to 1. The system parameters Lm, RL and Km are expressed in equation 2.4 and 2.1. Go to next slide. So an equivalent circuit of closed loop compensated Hall effect current sensors is derived based on the assumptions relevant from perspective of power electronic applications. So this is used to develop a model of the current sensor. Role of the compensator in the sensor is explained using the derived equivalent circuit and the block diagram model. In low frequency range, the compensator along with the Hall element plays a dominant role, while at high frequency the current transformer action takes place. Dynamic performance of the current sensor with the proportional and the PI compensator is analyzed. The sensor with the proportional compensator has inherent non-zero steady state error, while the PI compensator always results in zero steady state error for DC measurement. Even though the derived model represents low frequency behavior of the sensor, its use in the tuning procedure has major impact on the behavior of the sensor immediately after the rising edge of the step response. So choosing eta n is equal to 1 reduces the overshoot in the step response while having fast settling time. Tuning procedure based on analytical expression of the step response is proposed for PI compensator. A high value of omega n ensures fast dynamic response as well as good steady state performance. Right. Go to next slide. Next slide, next slide. So the power electronic current source produces reference step current and sinusoidal current in two different branches. So P1 to P2 and P3 and P4 respectively, right? So this is shown in the slide. So the conductors in these branches are mounted with screws and can be detached to insert the sensor under test. So the hardware includes a three-phase auto transformer, a step-down transformer, and diode bridge rectifier with electrolytic capacitor bank to produce a variable DC voltage VD across the terminals DC plus and DC minus. So auxiliary DC power supply of plus 15 volt, minus 15 volt, 0 volt, plus 24 volt are also required for internal gate drivers, protection cards, sensing cards, and a digital controller platform, etc. Right. So go to next slide. So the figure A shows three-phase auto transformer, step-down transformer, and a diode bridge rectifier with DC electrolytic capacitor bank CD to produce a variable DC voltage VD across the terminals DC plus and DC minus. Right. The internal power circuit of the current source is shown in the slide. That is figure B, 3.2B, for reference sinusoidal current and the step current generation. Right. So an IGBT terminal and a MOSFET terminal are connected in parallel to the DC bus. The circuit resembles a single phase H bridge voltage source inverter constituting power MOSFETs M1, M2 and IGBTs IG1, IG2, right? So the choice of using two different devices is explained in later, right? So power circuit of hardware setup, characterization of Hall effect current sensor. Figure A shows series connected auto transformer, step down transformer, and variable DC voltage VD. And figure B shows the circuit topology to produce reference step current ILS of T and the sinusoidal current I naught of T in the branch P1 to P2 and P3 to P4 respectively. So the load is an air core inductor L naught. And RCD over voltage clamp is connected across the IGBT lug, which is used to observe step current ILS of T in the branch P1 to P2. The MOSFET lug is protected with the DC coupling capacitive snubber C. Reference sinusoidal current I naught of T is observed in the branch P3 to P4. Go to the next slide, please. Okay. So the power circuit is reproduced in this slide to simplify the visualization. Right. It must be noted here that at the time only one type of reference current, step or sine wave, can be produced by the current source. So the hardware is configured in such a way that no modification is required to change over from sinusoidal current generation mode to step current generation mode or vice versa. So the branches P1 to P2 and P3 to P4 are screw mounted and can be detached to accommodate the current sensor under test. So typical value of insertion impedance of Hall effect current sensor used in power electronic applications is below 100 nanohenry. So it can be seen in the slide. Insertion of current sensor in the branch P3 to P4 does not affect the total inductance of the load significantly, as the load inductor L0 is much larger compared to the insertion impedance of current sensor. But the insertion impedance becomes comparable when the sensor is inserted in the branch P1 to P2 of positive DC bus plate and has direct impact on the total loop stay inductance of the DC bus. It causes large voltage overshoot across the IGBT during the turn off. Moreover, the positive DC terminal needs to be modified to accommodate the current sensor in the branch P1 to P2 and hence the positive and the negative DC bus terminals cannot be placed lateral to each other. So it further increases total loop stay inductance across the DC bus. A careful approach to design the layout of DC bus terminals and of the snuffer elements can be chosen properly to minimize the voltage overshoot across the semiconductor devices. Right. So go to next slide. So this is a symbolic representation of top view of hardware setup. The solid and dotted lines represent positive and negative DC bus plate respectively. IGBT and the MOSFET modules are placed carefully to reduce the loop inductance created by branch P1 to P2 of positive DC bus and negative DC bus terminals. So the layout of DC bus plates along with the connection of semiconductor devices is symbolically sketched in the slide. The layout of device ensures that additional stray inductance due to the branch P1 to P2 appears only across the IGBT terminal and not across the MOSFET terminal. So it is shown later that only the IGBT terminal is switched to observe a step current and undergoes large voltage overshoot during the turn off due to additional DC bus stray inductance. So considering this voltage rating of IGBT is chosen much higher compared to DC bus, while the power MOSFETs voltage rating is relatively low. So low voltage power MOSFETs have very low on resistance compared to those of high voltage rating. A silicon carbide diode is selected as the snuffer diode, right? Owing to its zero reverse recovery feature. It is shown in the slide. What are the advantages? What are the properties in the reverse recovery and the snuffer diode is shown in the next slides, right? So size of two different devices and the working principle of the circuit. Right. So step electric current may be produced as either rising or falling current Producing perfect step change in an electric current is impossible due to inherent stay inductance associated with current carrying elements in the circuit, but the duration of change can be minimized to emulate the step current, though it results in very high di by dt, producing large voltage drop over the inductive path, which can damage the electric circuit elements. So, a non-destructive method is proposed to generate both rising and falling step current with rise or fall time less than 200 nanosecond and adjustable step current value, right? So its di by dt can be varied by using suitable snubber capacitor. Okay. Go to next slide. So this is a three-dimensional representation of the hardware setup in step current generation mode. So use a cut in the positive DC bus to accommodate the current sensor in the branch P1 to P2 increases the loop area and in turn the total DC bus stray inductance. So these are shown in the next slide. Go to next slide. Please go to next slide. Okay. So the equivalent circuit in the slide figure 3.6b. Here LS represents total stray inductance. It includes the insertion impedance offered by the current sensor also. The current ILS of T flowing in the branch P1 to P2 is the record simulates for step response measurement of the current sensor under test. So the semiconductor switches can be switched in the particular sequence to generate either falling or rising step current. The operation of this circuit is explained will explain the following slides to generate the step current, right? Go to the next slide. So here 4 modes of operation is there. So mode 1, all the 4 switches are off. The capacitor gets charged to DC bus voltage. To avoid large inverse current, the DC bus voltage is increased slowly using auto transformer at the AC input side till it reaches VD. Okay. So mode 2, the top IGBT, IG1 and the bottom MOSFET M2 are switched on. The total inductor L0 starts getting charged and the current I0 of T increases linearly. So it is expressed in ILS 0 is equal to VD by L0 into T on, right? This is the equation number 3.1. So where T on is the on period of IGBT1. So mode 3, the load current I0 of T is sensed using a current sensor. When it attains the specified value ILS not, the IGBT IG1 is turned off. As soon as the voltage across IG1 rises to DC bus voltage VD, the diode D4 starts freewheeling the inductor current I0 and the IGBT current IC1 starts falling. So owing to a very small turn off time of the IGBT used in the hardware, the DC bus current ILS can be assumed to stay a constant at ILS not till IC1 falls to 0, right? So fall time of IC1 is governed by the turned off characteristics of the IGBT and is neglected to simplify the further analysis. When IG1 starts turning off, the snubber diode D on turns on and C starts getting charged from its initial pre-charged voltage VD till ILS, right, comes down to 0. So the voltage VCE1 across IG1 is equal to the capacitor voltage VC0V as long as diode is conducting. So the freewheeling diode D4 along with L0 appears as short circuit after IG1 turns off. So mode 4, the snuffer diode D0V stops conducting. The capacitor C0V starts getting discharged through the resistor R0V till its voltage comes down to the DC bus voltage VD. So T2 on-state voltage drop across M2 and D4. The freewheeling current I0 of T also comes down to 0 in a while, right? So the above 4 modes complete the sequence to generate the falling step current. It is a single pulse operation and the modes are not repeated, right? The falling step current is observed in mode 3 and the response may captured in a high bandwidth oscilloscope in single sequence capture mode. So as it is one cycle process, the power consumption during step current generation is not considered while designing the hardware setup, right? So the factors governing the characteristic of falling step current in the mode 3 are analyzed. So at the start of mode 3, the current ILS of T and ILS 0 and IG1 is turned off. Go to next slide. So the diode D0V starts conducting till ILS of T comes down to 0. The equivalent circuit during the delay of ILS of T can be represented as the slide, the figure 3.8. So the switching transients of diodes and IGBTs are ignored during the analysis. So assuming that ILS of T starts falling at T is equal to 0. The equivalent circuit in figure 3.8 can be used to derive the expression of ILS of T and the VC0 of T valid for conduction interval of D0V, right? So the equation 3.4 omega naught is equal to 1 divided by root of LS into C0V. Go to next slide. The fall time TF is calculated when ILS of T comes down to 0 and D0V stops conducting. It results in equation 3.5. The gate pulses G1 to G4 along with I0 of T, IC1 of T, ILS of T, VC1 of T. So these are shown in the next slide, right? Go to next slide. So this is the gate pulses G1 to G4 along with I0 of T, IC1 of T, ILS of T, VC1 of T, IC0V of T and IC0V of T. So during the 4 modes, right? So the capacitor COV is pre-charged to VD, putting VC0V is equal to VD, right? So in practical implementation, the DC bus voltage VD is fixed and the stay inductance LS depends only on the layout arrangement on the devices. The bus plates and the sensor insertion inductance. The peak currents ILS 0 is fixed and must be below the rated current of the IGBT. The equation 3.8 C0V is left to be decided to generate a current of peak ILS 0 with fall time of TF, right? Go to next slide. Here A shows the variation in the fault time TF with the overshoot in voltage across IG1 for a fixed value of peak current ILS 0. A family of curves is plotted for different values of ILS 0 using the equation 3.10. Right? The designer may first decide the permissible overshoot based on the device voltage rating. So with this overshoot, minimum value of fault time is found out with the curve of the largest ILS naught. So using figure B, a suitable value of the capacitor is selected for a fault time greater than or equal to the value of TF. So the capacitor COV experiences high dV by dt just after IG1 turns off completely, right? Selection of ROV. The resistor ROV of the RCD snapper comes into picture in the mode 4 when COV starts getting discharged, right? Go to next slide. So in this slide is shown that this RCD snapper is used in generation of reference sinusoidal current, also using pulse width modulated power converter configuration, right? So this figure shows so already we see figure 3.3, right? So to produce falling step current is used to rising step current generation, right? So in this case, the sense of deduction of the currents ILS of T and I naught of T is reverse compared to that in falling one. This is shown in the slide, right? So here mode 1, mode 2, mode 3 and mode 4 operations are there. We will get falling step current, the equations governing in the characteristics of ILS of T. Go to next slide. So the equations 3.11, 3.12 and 3.13. The procedure to select COV for a desired rise time TR is similar to that of previous one and can be decided using these equations for a particular value of ILS 0 and rise time, right? So rise time TR is independent of ILS naught. So waveforms of the gate pulses. Go to next slide. Go to next slide, please. So this is the waveforms of the gate pulses G1 to G4 along with I naught of T, IC1 of T, ILS of T and VCE4 of T during the 4 modes in generation of rising step current. So go to next slide. So this is a hybrid PWM principle and its frequency spectrum. So here this is an equivalent circuit. The winding resistance of L naught is denoted by R naught. CD is the capacitance of the DC bus, electrolytic capacitor, right? So go to next slide. So this is a average model of the inverter modeled with hybrid PWM method and is similar to sine triangular unipolar PWM method. The average output VAB Okay. So VAB of t is equal to m of t into VD. This is the equation 3.14. Taking Laplace transformation on both sides with zero initial conditions, we will get the equation 3.15, right? So the open loop transfer function of the closed loop system is shown in the slide. So we will get the equation 3.16. So go to next slide. Okay. Next slide. So this is adaptive scheme for online change in frequency of the output current, and the block diagram of frequency adapted proportional resonant controller based on two integrations in continuous time domain. Okay. Go to the next slide. So this is the H-bridge hardware design. Go to next slide. Next. So these are the specifications of various components used in hardware setup, right? Go to next slide. Next. 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 Okay. So this is experimental waveforms of step current LS of T produced in branch P1 to P4 and IGBT voltage overshoot for different values of snapper capacitor. Okay, go to summary slide. Okay. So the power electronic converter based current source is designed to produce falling step current, right, and the rising step current and the sinusoidal current for performance validation of Hall effect current sensors used in power electronic applications. A circuit topology is proposed to generate all these currents without any modifications in the hardware setup of the current source. The configuration of the hardware setup facilitates insertion and removal of the sensor under test. The circuit resembles an H-bridge voltage sensor inverter consisting of power MOSFET leg and an IGBT leg. By modulating the switches in a particular fashion, either of these three currents can be produced in the designed section of the setup. For sinusoidal current generation of hybrid PWM technique is suggested to use to modulate the switches to a single phase voltage source converter to reduce total switching losses. So the scheme is proposed for online change of magnitude and the frequency of the reference sinusoidal current. The magnitude and the frequency of the sinusoidal current is changed online like a voltage function generator. So due to limitation of the current rating of the MOSFETs used in the hardware, the peak of the sinusoidal current is limited to 75 amps in the experiments. Experimental results are shown for sinusoidal current with 75 ampere peak and the fundamental frequency varying from 1 Hz to 1000 Hz. THD of the controlled output current around 2% in low frequency range and goes up to 5.1% near 1 kilohertz. So the hardware setup consumes 315 watts active power from mains power supply while producing sinusoidal current of peak 75 amp and the frequency 50 Hz. So due to low power and the current consumption from the mains power supply, the current source can be used even in a small laboratory or test premises to produce continuous 75 ampere peak sinusoidal current, right? So thank you. Scope of future work is also right? So experimentally obtained the minimum value of the step transition time of the step current produced by the power electronic converter based current source is 170 nanosecond, right? The setup can also produce non-sinusoidal current waveform by combining fundamental and few of its harmonics, which can be used to characterize Hall effect current sensors under harmonic distortion, right? So it will also reduce the overall losses in the system during sinusoidal current generation, right? Thank you.
Thank you, sir.
Thank you.
Sir, shall we conclude with this session, sir?
Okay, please.
Okay. Dear participant, do you have any questions? Yes. Sir, where are the Hall effect sensors are used, sir? One participant who asked this question through a chat box. Where are Hall effect sensors are used?
Where are?
Hall effect sensor are used. Where they are used for Hall effect sensors?
Where they are used? Sir.
Yes, sir. Yes.
Yeah. So a lot of applications are there.
Yes, right, sir. You are right.
I already told in many slides. Okay. So power electronic
Okay.
converters.
Okay,
Right.
sir. Okay, right, sir. Now you want to for conclusion, sir. So thank you, sir. Thank you. Thank you for your valuable information, sir. Okay. Thank you, sir.
Thank you,
Yes,
sir.
sir.
Thank you.
Okay.
Thank you.
On behalf of our PSR management, we could like to thank our beloved chief guest, Dr.S. Selvaperumal, Professor Syed Ammal Engineering College, Ramanathapuram, for his gracious presence and delivered the technical contents about compensator designed for closed loop Hall effect current sensors, power electronics converter, and a characterization of Hall effect current sensor. Once again, I thank for your valuable technical presentation, sir. Thank you, sir.
Thank you very much. I would like to thank management, principal, and Professor P. Karpasamy for gave the wonderful opportunity to deliver the lecture on the topic of Hall effect sensor for power electronic applications.
Thank you very much, sir. Thank you very much for your.
Thank you very much.
Thank you.
Thank you.